so the names that are there. As the title states, this is about prediction, input prediction. But first I have to talk about latency. Most interactive systems have a delay between user inputs and the corresponding interface feedback. That's called latency or lag. Latency has a number of sources, both hardware and software. For instance, the time it takes for the input to be recognized or the time it takes to render the visual feedback. The sum of all of these intermediate delays is typically between 50 and 200 milliseconds for direct touch these days. On the other hand, previous work in HCI have shown that delays as low as 10 milliseconds still cause direct touch pointing performance to degrade, even when that delay is not noticed by the user. And we can't just wait for hardware to catch up with latency. Hardware improvements do help and will keep helping with that issue, but it will probably not solve the problem in the foreseeable future. Some of the sources of latency depend on the software complexity of the task at hand. Think very rich visual feedback in 3D video games. And we expect that as hardware keeps improving, that complexity will keep increasing as well. Similarly, most displays are refreshed every 15 milliseconds or so, which is already above the performance threshold found in previous work. So this is a part of latency that hardware can solve. For everything else, there's input prediction. Input prediction is a software process that consists in displaying visual feedback not for the last detected input, but for an input that is expected to be detected in the near future. For touch, that means to extrapolate or predict the trajectory of the user's finger in order to estimate the current finger location. This method, technically, can compensate any amount of latency provided that you have accurate predictions. There's already a quantity of research on such prediction methods and a number of patents from major players such as Microsoft, Apple, Samsung, and so on. Some are already implemented in commercial products. Existing methods are based on Taylor series, Kalman filters, quadratic curve fitting, or specific heuristics applied to the speed and acceleration of the current finger movement. However, all of these existing methods actually only correct a small fraction of the total latency in the order of 5 to 30% in the best cases. This means that most of the adverse effects of latency on performance remain, even when prediction methods are applied. This is because the further the extrapolation, the higher the chances of prediction errors. These errors in previous work have been measured in terms of distance-based metrics, such as root mean square error or mean or maximum distance. The problem we see with these metrics is that they convey very little of what the user actually experiences when a prediction method makes an error. Let's take root mean square error, which is the most commonly used error metric in previous work. The way it works, simple latency like that, will yield error measurements similar to a mistaken orientation of the predicted point, or to dynamic errors such as excessive noise in the prediction or sudden jumps in the predicted location. We hypothesize that already these example problems are quite different from each other in the perspective of the user, and yet today's typical error metrics will not differentiate them. As a result, the way input predictors are designed and implemented will not explicitly differentiate these sources of errors. So in order to better understand this problem and to see how far we are from total compensation of latency, we ran a controlled experiment on a direct touch tablet. We implemented today's most common prediction methods from actual patents, but we set them up to reduce the overall latency below noticeable levels, 10 milliseconds, as opposed to only compensate up to 16 milliseconds. We instructed participants to perform 3 tasks typical of direct touch interfaces: drawing, dragging, and panning. So drawing consisted first in following a set of shapes displayed on the application background. And participants were also encouraged to try out free drawing. Dragging consisted in bringing a blue square inside a green square in a typical fits-like task. And panning consisted in freely navigating in a virtual environment, which we abstracted as a map of colored squares. In all three tasks, participants were instructed to explore different speeds, accelerations, directions, curvatures, and so on. During and after each condition, they were asked to verbally comment and describe every behavior that differed from a hypothetically perfectly responsive visual interface, and to rate each of these problematic behaviors on a scale from not disturbing at all to unacceptable. Note that the participants were not given any detail on the way the predictors worked, even when they asked. So we gathered around 30 strokes per participant, predictor, and task, which indicates that participants did explore a number of possibilities in each condition, and about 1.6 comments, in average, per participant and condition. We analyzed these comments using thematic analysis, which is a method to categorize verbal or written feedback into semantic codes. During this process, which took us months, the whole set of comments was passed through every time a new code was proposed, discarded, split, or merged, depending on its relevance and redundancy. This resulted in 30 codes, which we classified into 4 categories. Side effects were actual descriptions of spatial accuracy errors, such as the cursor's lagging behind or the trace doesn't go in the right direction. So that's what we wanted in the first place. Then there were consequences on visual perception or on the feasibility of a task, such as I don't get what's happening or it makes me slower, that sort of things. These were sometimes reported along side effects and sometimes not. Participants often provided context with side effects or consequences, like at the beginning of a movement, when I accelerate or when I turn. And finally, participants sometimes felt like telling us when something was working well or not that bad. That was not part of instructions, but still interesting to report. In what follows, I will focus on the side effects, which were the main point of this study. We identified 7 of them that I will now briefly illustrate. Please note that some of them will appear exaggerated in this video for illustration purpose. So, lateness side effects were perceived as late or slow to react to the actual movement. Over-anticipation side effects were perceived as too far ahead in time or overreacting to the finger movement. Wrong distance side effects were perceived as distinguishably far from the finger's location. Wrong orientation side effects were perceived as not going in the same direction as the finger motion. Jitter side effects were perceived as trembling around the finger location. Jump side effects were perceived as jumping away from the finger at times. And in spring side effects, the prediction appeared as if attached to the finger with a spring, or to yo-yo around the finger. Note that all of these side effects were mentioned by 11 or 12 participants each. With these results, both input strokes and comments, we defined a set of spatial accuracy metrics corresponding to each of these side effects, so existing and new predictors can be evaluated for each of the problems that the participants identified. More precisely, our goal was to model the probability to notice each side effect using actual and predicted coordinates only. So first we discarded the 5% shortest and longest strokes in terms of duration. The shortest ones barely used prediction, and the longest ones might have added extra delay in their visual response. Then each individual stroke was applied a function that we call a metric that we designed for a specific side effect. So each side effect had its own metric function. The results of these functions were averaged over the whole strokes dataset in order to produce the magnitude of the corresponding metric for each predictor. Finally, the probability to notice a given side effect was calculated as the number of times this side effect was reported for a given predictor, divided by the number of times it could have been reported. So our metric functions were designed through a long trial and error process that I will not discuss here, but it's discussed in the paper. Just trust me when I say that the obvious solution often doesn't work. These metrics were designed with 4 goals in mind. Their formulation had to relate to the description of the reported problem. The formula had to be as simple as possible with minimal and understandable parameters. It had to be robust to parameter variation, so not depend too much on parameter tuning. And it had to produce a positive and linear correlation with the side effect probability, so the resulting values could be compared directly. Now I will explain briefly how these metrics work and what they measure. This is going to be tedious, so please bear with me. Our metrics mostly worked frame by frame for a given stroke and used 2 vectors. The current direction of the actual user movement, here the vector f, and the difference between actual and predicted coordinates, here the vector d. The lateness metric works by detecting predictions that are significantly behind the direction of the movement. That is, when the orientations of vectors f and d differ beyond a certain threshold. The magnitude of the metric is defined as the average distance between actual and predicted coordinates for such points. With a threshold of 90 degrees, we obtain an R-square of 0.9, which is better than traditional metrics. The over-anticipation metric works exactly the opposite. It calculates the average distance between actual and predicted coordinates when the angular difference between f and d is below a certain threshold. With the same threshold as before, we obtain an R-square of 0.89, which is now much better than traditional metrics. Despite a straightforward label, we could not formulate a metric for wrong distance that would fit better than the metric for over-anticipate. However, over-anticipate and wrong distance were by far the most correlated side effects. We hypothesized that they were interchangeable, or at least that a number of wrong distance reports could have been described as over-anticipation by different participants. Still better than traditional metrics. The wrong orientation metric calculates the mean angular difference between the orientations of the vectors f and d when that difference is below a certain threshold. We obtained an R-square of 0.76 with a threshold of 90 degrees, again notably better than traditional metrics. The jitter and jumps metrics use the same process with different parameter values. First, the predicted coordinates are smoothed using a zero-phased shift filter with a certain cutoff frequency. Then the magnitude of the metric is calculated as the average distance between raw and filtered predicted coordinates. With cutoff frequencies of 0.15 and 0.2 Hz, we obtained R-squares of 0.84 for jitter and 0.99 for jumps. Note that here, traditional metrics provide acceptable R-squares for these side effects, but with a negative correlation or a negative slope. This means that selecting a predictor based on their lower scores could actually increase the risk of observing jitter and jump behaviors. Finally, the metric for spring effect was calculated by counting the local extrema in the second derivative of the distance between actual and predicted coordinates over time. This yields an R-square of 0.77, once again much better than traditional metrics. So that's it for the metrics. Sorry about that. Now, why does this matter? First, we showed that existing prediction methods and error metrics are poorly adapted to the spatial accuracy issues that really bother users and to which extent. We produced a set of metrics that model how often these issues are observed using only the geometric properties of actual and predicted coordinates. That means that interaction designers can now compare existing or new predictors for specific side effects and without requiring systematic user feedback. The equations of these metrics can also inform the design of new predictors by precisely formulating what behaviors should be avoided, the trade-offs between these side effects, and how much latency can be corrected before they become noticeable. Up until now, designing a new predictor meant that every time you explore a new method or a set of parameter values, you had to systematically evaluate it with a full user study. But now the input logs that we obtained and that we will share publicly on our webpage can be used during the early stages of new predictor design to quickly evaluate side effect magnitudes. And we encourage anyone interested to simply grab them and reuse them. In the later stages of predictor design, a simplified version of our experiment protocol, without the tedious bits of comments gathering and analysis, can be used to gather new input data specific to that new predictor. And the full experiment protocol, including comments analysis, can be reused for other input modalities. So finally, our future work involves designing new predictors for direct touch using these results, and extending this work to other input modalities such as VR or meter gestures. This concludes my presentation. I encourage you to have a look at the paper for more thorough discussions and insights on how participants formulated their comments, what they preferred, and how predictors and tasks affected their perceptions. Thanks a lot for your attention.
Thank you, Mathieu. We have time for questions. Raise your hands for questions, and our student volunteers will come to you with microphones. Okay, people are doing so. I have a quick question. I'm doing research regarding some pen computing, so I'm wondering if your model and some regression data can be directly used for the drawing with the pen.
That's a very good question. The thing with the finger is that we expect that it actually probably hides some of those errors that happen below it. Of course, I would expect that doing the same thing with a pen would be even more demanding because there's a clear point, a clear visible point that is the tip of the pen that you can immediately compare to the prediction, and this might makes it just make the precision requirements much higher. So I would say, it would be interesting to run the same protocol for pen input and see how it affects our results. Hopefully the metrics should not be too different, but probably there would be a shift up in terms of noticeability. At least that's what I hypothesize.
Thank you.
Thank you.
Any questions? Yes.
Hi, Tomer Moskovich, Nancel.
Hi.
Great talk. So I wonder if you have any insights about, now that you have these new metrics, how the existing methods do. Are they doing better than we thought, worse than we thought? And are there any of them that stand out as being better than the rest, now that you have this better metric to investigate them with?
You mean the existing prediction methods?
Yes.
Yeah. Well, overall they all behave as they should, which is they work well for the amounts of latency that they are designed to correct. So that's usually 1 or 2 frames ahead. We did actually run simulations on how they would fare while correcting more latency with our input data set. That's where, it's not really that one of them sticks out. It's more like trade-offs really appear. Some of them start being much closer than what you'd expect, but will start jittering like crazy. And some of them remain really smooth, but will keep some lag all along the way.
Thank you.
And we do discuss that in the paper.
Yes, one more question. Okay. Yeah, a lot of thanks to you. Yes.
Thank you very much.